We start our discussion on the first module of chapter 9. In the first chapters, we have already seen that we can define a measure, namely Lebesgue measure, on the set of real numbers, which extends the notion of lengths of intervals. And the question is that whether we can introduce the notion of length or a measure on an abstract set. Now, in order to do that, the first thing we need to do is that we have to define certain suitable classes of sets, so that we can define our desired measure. So, we will first start with certain set theoretic classes and we will establish some of their properties. And with this we go to our first slide. We start with our first definition. Let X be a non-empty set. A non-empty class R of subsets of X is said to be a ring if the first condition, if A and B belongs to R, then A union B belongs to R. Second condition, if A and B belongs to R, then A minus B belongs to R. That is, the class R is closed under union and difference. It is easy to observe that since the class is closed under union of two sets, so we can say that it is also closed under union of finite number of sets. Also, from the definition, it clearly follows that A delta B, where delta stands for the symmetric difference. So, this we define as A minus B union B minus A. So, this also belongs to the ring R, and A intersection B, which can be written as A union B minus A delta B, this also belongs to R. If the ring R has the property that for any set A belonging to R, the complement also belongs to R, then we say that R is an algebra. So, in other words, R is an algebra if and only if it contains the whole set X. Obviously, every algebra is a ring, but the converse is not true. For example, if in an infinite set, if we take the collection of all finite subsets, then it is a ring, but not an algebra. Also, it is quite easy to prove that the intersection of a collection of rings on a set X is again a ring, and if E is a class of subsets of X, then the intersection of all rings containing E is again a ring, which is called the ring generated by E and is denoted by R E. Next, we are going to see some properties of this particular class R E. Lemma 1. Every member of R E can be covered by a finite number of sets from E. So, for example, if every member of E is finite, then every member of R E will also be finite. If every member of E is countable, then every member of R E will again be countable. How we prove it? Let R star be the collection of all those subsets of X which can be covered by a finite number of sets from E. See that if we take two members A and B from R star, then A can be covered by say m number of sets from E and B can be covered by say n number of sets from E, and obviously A union B then can be covered by at most m plus n number of sets from E. And it is easy to see that as A minus B is subset of A, so A minus B is already covered by a finite number of sets from E. So, R star forms a ring containing E. Now, by our definition, RE is the smallest ring containing E. So, this shows that RE must be subset of R star, and consequently every member of RE can be covered by a finite number of sets from E. Now, we consider the cardinality of the class RE. First, it is very easy observation that if the original class of sets E is uncountable, then since RE already contains E, so RE is also uncountable. We will prove that if the collection E is countable, then RE is also countable. How we prove it? So, again we start the proof in this way. For a class of subsets C of x, let C star denote the collection of all possible finite unions of all possible differences of members of C. Then C countable implies that the collection of all differences of members of C is also countable, because any difference can be written in the form A minus B, with which we can relate the pair AB. So, in that sense the collection of all differences of members of C is a subset of C cross C, and C cross C is countable. Now, see that we are taking finite unions of all possible differences. Now, we know that if a set is countable, then the collection of all finite sequences formed by the elements of that set is also countable. And if we use this fact, then it now follows that C star is also countable. Now, let phi belongs to C. Observe that for any set A belonging to C, we can write A as A minus phi. So, it belongs to C star, and so phi belongs to C implies that C is subset of C star. Without any loss of generality, let us assume that the class of sets E contains the empty set phi. Now, let us define inductively a class of sets in this way: E0 equal to E, E1 equal to E0 star, En equal to En minus 1 star, and so on. Observe that as phi belongs to E, so E is subset of E star, that is E1, this is subset of E1 star, that is E2, this is subset of En. So, we have a monotonically increasing sequence of collections of sets. Since E is countable and we already know that the start of a set is countable, so each En is also countable, and this implies that union n equal to 1 to infinity En being countable union of countable sets is also countable. Obviously, E is subset of the whole union n equal to 1 to infinity En. Now, observe that how we constructed E1. E1 is the collection of all finite unions of differences of members of E. Now, see that Re is the smallest ring containing E. So, it is already closed under difference and finite union. So, E1 is a subset of Re. Similarly, E2 is subset of Re, and in particular every En is subset of Re. So, we have union n equal to 1 to infinity En subset of Re. We are now going to show that this collection union n equal to 1 to infinity En is itself a ring. For that, let us take two sets A and B from the whole union. Then from the definition, we can find two indices I and j such that A belongs to Ei and B belongs to say Ej. I and j are two natural numbers, and without any loss of generality we can assume that I is less than j. Then both the sets A and B belongs to Ej. Consequently, the difference A minus B belongs to the set Ej plus 1, and this is again subset of union n equal to 1 to infinity En. Now, observe that if we consider the union A union B, we can rewrite it as A minus phi union B minus phi, and it also belongs to Ej plus 1, and so belongs to the whole union. And this shows that union n equal to 1 to infinity En is closed under finite union and difference, and this is a ring. We already have seen that E is a subset of this collection. So, union n equal to 1 to infinity En is a ring containing the class E. Re is the smallest ring containing E. So, we must again have Re subset of union n equal to 1 to infinity En. But we have already seen that the reverse inclusion is also true. So, combining we have Re equal to union n equal to 1 to infinity En. Since the collection union n equal to 1 to infinity En is countable, so this finally proves our assertion that Re is countable. We now start the definition of the second class. A non-empty class of subsets S of a set X is called a sigma ring if it is closed under difference and it is closed under countable union, that is if we take a sequence of sets A n from S, then union n equal to 1 to infinity A n also belongs to S. It is easy to again observe that a sigma ring is closed under countable intersection. A sigma ring is a ring, but the converse is not true, because if we take the collection of finite subsets of an infinite set, then it forms a ring, but it does not form a sigma ring. As in the case of rings, it is an easy observation that intersection of a family of sigma rings is again a sigma ring, and we define S E to be the smallest sigma ring containing a class of sets E, and this is called the sigma ring generated by the class of sets E. As in the case of R E, we can prove a similar result, that every member of S E can be covered by a countable number of sets from E. The proof is done in the same way, that is, we take as S star as the collection of all subsets which can be covered by a countable number of sets from E. Then we can show that S star forms a sigma ring, and since S E is the smallest sigma ring containing E, so S E should be subset of S star, and from this fact the conclusion follows. A sigma ring S is called a sigma algebra if and only if the whole set X belongs to S, and of course, it means that it is closed under complementation. Now, recall that we have noted that if E is countable, then R E is also countable. Now, for S E, this result does not hold. The easiest example is that if we take E as the collection of all singletons n, where n runs over all natural numbers, then E is countable, but S E is the power set of n which is uncountable. Coming to sigma algebra, like ring, we can show that every sigma algebra is a sigma ring, but the converse is not generally true. For example, the collection of all countable subsets of an uncountable set is a sigma ring which is not a sigma algebra. Finally, we prove a particular result in this module, which we will use later in this chapter. For any class of subsets E and a subset A of the set X, we can prove that S E intersection A is equal to S of E intersection A. Here E intersection A stands for the collection of all sets of the form B intersection A, where B is a member of E. The proof goes like this: denote by D the collection of all subsets of X which can be written in the form B union C minus A, where the first set B belongs to the sigma ring generated by E intersection A, and the set C belongs to S E. we can show that the collection D is closed under both difference and countable union, and so it forms a sigma ring. Now, if E belongs to E, then we can write the set F as union of two sets F intersection A union F minus A. See that the first set F intersection A belongs to E intersection A, which is subset of S E intersection A by our definition, and this shows that the set F also belongs to D, and hence the collection E is subset of D. So, D is a sigma ring containing the collection of sets E. Since AC is the smallest sigma ring containing E and D is an arbitrary ring containing E, so it follows that AC is contained in D. Now, it is quite clear that since AC is subset of D, so the collection of sets AC intersection A is subset of D intersection A. And from the construction of the class D, we note that D intersection A is actually the collection S of E intersection A. So, we have the one inclusion that AC intersection A is contained in the sigma ring generated by E intersection A. So, the result will be complete if we can show the reverse inclusion. Now, observe that for every F belonging to the class E, F intersection A belongs to AC intersection A, since E is subset of AC. So, this shows that E intersection A is subset of AC intersection A. This is again subset of S of E intersection A. Now, since AC intersection A is itself a sigma ring, because we can actually show that if S is a sigma ring and we take the intersections of all members of the sigma ring with a fixed set, then the resulting class is also a sigma ring. So, AC intersection A is a sigma ring and S of E intersection A is the smallest sigma ring containing E intersection A. So, we get the reverse inclusion that S of E intersection A is contained in AC intersection A, and this proves the theorem. So, to summarize, what we did in this module is that we have introduced two classes of sets called rings and sigma rings. A ring is a class of sets which is closed under difference and finite union, and a sigma ring is a non-empty class of sets which is closed under difference and countable union. We have seen that from a given class of sets E, we can generate a ring or a sigma ring, which we denote by RE or SE. We have also seen some of the basic properties of these generated classes, and with this we finish this module.